So here's our flowchart for photons. We've seen that light has both wave and particle characteristics. If you think of light as a particle, you can think that the particles are photons, and each photon particle has an energy that's given by this equation over here. All right, now how about electrons and other particles with mass? Well, all this time in chemistry and physics, you've been thinking of those as particles, but wave-particle duality says that they also have wave characteristics. So now let's do a flowchart for electrons and other particles with mass. Electrons and other things with mass. So we can start by focusing on the wavelength. Now it turns out that this wavelength is related to the momentum. Do you remember the symbol for momentum from last semester?
P?
Yeah, that's good. Lowercase p. And it turns out this is the formula that relates the momentum and the wavelength of the electron or the other particle. And what's h again? Planck's constant. Okay. Let's think for a second about velocity, another concept from previously. What's our symbol for velocity? And what's the unit for velocity? Good. What's the equation that relates momentum and velocity?
P equals mv.
Right. The momentum is a kind of measure of how much motion an object has. The momentum is a way of measuring how much motion the object has. Well, you can measure the motion as mass times velocity. Because the more mass you have, that also gives you more motion in the sense that it's harder to stop you. That's a formula from back in last semester. So by the way, we can figure out from this formula what the units are for momentum.
Units for second.
What's the units for mass?
Sorry, grams. Kilograms.
The standard units would be kilograms. So maybe for a second you thought this was meters, right? And velocity is meters per second. So we always have to distinguish between letters that stand for concepts and letters that stand for units. All right, so we can always figure out the units for momentum from the definition of momentum here. This is the formula for momentum we saw last semester. By the way, this formula only works when you don't have relativity. When relativity is important, there's a different formula for momentum. That happens when you're moving at very high speeds. This formula only works at low speeds. Now, you don't really have to worry about that much because your course isn't covering momentum. So you're only expected to know momentum at they would call that non-relativistic momentum. The reason I'm mentioning this, though, is that you'll probably see a bunch of problems where they'll say something like, assume that the speeds are non-relativistic, or assume the speeds are low. Well, they're just saying that to cover themselves, to explain why they're using the non-relativity formula. But they're always going to say that in your course because you're not learning about the relativity formula. Okay, so this is the formula we'll use for momentum. So let's solve this equation for wavelength. What do we get if we solve this equation for wavelength?
H over P.
Good. Now, remember, what does this stand for? It stands for something weird. It's the wavelength of a particle with mass, like an electron, or a proton, or a neutron, or even my chalk holder. All particles actually have wavelengths, or a baseball. All particles actually have wave characteristics, and they have wavelengths. That's that wave-particle duality idea from modern physics. And this should seem weird because it doesn't accord with our common sense. This doesn't seem like a wave, but it has wave characteristics. The guy that came up with this idea, I think, was de Broglie, if I'm pronouncing it right. Doesn't look like it's pronounced de Broglie, but I think that's the pronunciation. So this is the de Broglie wavelength, and you'll see that term used in your homework and on exams. So if they ask you for the de Broglie wavelength, this is what they're asking you for. Now you can already start to see why we need two separate flowcharts, because this is not the de Broglie wavelength. This is the wavelength of a photon. That's not de Broglie. De Broglie is the wavelength of a particle with mass, like an electron or something like that. So this is our de Broglie wavelength. So if they ask you for the de Broglie wavelength, they're using this flowchart, not this one down here. People very often get these things confused. Okay, now let's say that your mass is big. Does that mean your momentum is big or small?
It means that your momentum is big.
So does that mean that your wavelength is big or small?
It's small.
Because a big denominator means a small wavelength. Does that mean your wave characteristics are important or not important?
If your that means your wavelength characteristics are not.
It means you behave like a particle. Good. It's particle-like. On the other hand, if your mass is small, then your momentum would be small. Well, a small denominator here would give us a big lambda. And we said that big wavelengths mean that you're very wave-like. Your wave characteristics are important. For example, let's think about an electron. Does an electron have a big mass or a small mass? So the electron would be down here, and it's going to end up then wave-like or particle-like.
Wave-like.
Yeah, that doesn't mean the particle characteristics can't be important too, but this does mean we can't ignore the wave characteristics. The wave characteristics are important here. An electron has important wave characteristics, even though sometimes we think of it as a particle. On the other hand, think about, say, the chalk holder. Well, does that have a big mass? You don't usually think of this as a big mass, but compared to the electron, the chalk holder has a huge mass. Compared to the electron, anything in ordinary life has a big mass. So the chalk would have a big mass, which means that it basically behaves like a particle. So that's, again, the reason that we don't notice the wave-particle duality. The wavelength here is so tiny, it has no practical importance. That's what's called, that's a term you might need, the correspondence principle. The correspondence principle is that the predictions of modern physics should correspond to classical physics in ordinary situations. The predictions of modern physics should correspond to what classical physics would say in ordinary situations, because otherwise we would have noticed modern physics a long time before 1900. It would just be part of our ordinary experience. The reason that we didn't notice this wave-particle duality before is because until 1900, people weren't paying very much attention to electrons. They weren't paying attention to things that were very small. They were only paying attention to things that were relatively big, like baseballs and chairs and chalk and stuff like that. That's a term you might even have to explain on a thought question on the exam. So the correspondence principle is, in ordinary situations, that is, things that have an ordinary mass, modern physics makes the same predictions as classical physics. That's why we didn't notice modern physics sooner. It's only when you are outside the realm of ordinary experience at very small masses that modern physics is important. So even though modern physics says that the chalk has wave characteristics, it also says that the wave characteristics are so small that we would never notice them. What does it mean that an electron has important wave characteristics? What would the wave characteristics be important? Well, remember the other topic that you're covering this week that you're going to watch the videos on is interference. And you're going to see, for example, how light waves interfere with each other. For example, you'll see if there's two different sources of light waves, then they can sometimes interfere constructively and they can sometimes interfere destructively. And that gives you a pattern of bright and dark spots. But it turns out, suppose you have two different sources of electrons. Well, since the electrons act like waves, the two different sources of electrons can also interfere constructively and destructively. And that means that the detector will sometimes detect a lot of electrons and sometimes detect no electrons. And that's not something you can interpret in terms of particles. You wouldn't think of particles as being able to interfere destructively with each other. It really is important that electrons have this wave-like property. That explains why they can interfere with each other like a wave does, which you wouldn't expect for a particle. Okay. What's our symbol for kinetic, well, let's just say K for kinetic energy. What's our unit for kinetic energy? That's right. Now, maybe it might be convenient sometimes here to use electron volts again, but the standard unit is joules. And what's the equation that relates kinetic energy and velocity? Okay. All right. that might be as much of this flowchart as we're going to go through today for the electrons and particles with mass. You might see some homework problems where they ask you to say, calculate the energy of this electron. And what they usually mean is the kinetic energy. They don't say that, but if they're not really being specific about what energy they're talking about, especially a free electron, a lot of times they're talking about the kinetic energy of the electron. So sometimes they'll just say energy when they mean kinetic energy. But now we can compare these two flowcharts, because both of the flowcharts show you how to go from wavelength to energy. And those are things that you're definitely going to have to do on the test and the homework. It's a much smaller path for a photon. The photon's wavelength gives you the frequency, and then we use Planck's constant to find the photon energy.